All right, lastly, we'll look at forms of the integrand having the square root of x squared minus a squared. Again, if you can use a simple substitution, that's usually always the best bet. But if you don't have that, if you have root x squared minus a squared, you could check and attempt to use x equal a secant theta. And then dx would be a secant theta tangent theta d theta, because the derivative of secant theta is secant theta tangent theta. So dx will be replaced with a secant theta tangent theta d theta, and your radical, having x squared minus a squared underneath, will be replaced with the absolute value of a tangent theta. All right, again, you want to be drawing your triangle. Once you do the substitution, you're going to simplify the expression, and then hopefully that integral is easier than the integral that you had to begin with. And lastly, because you've drawn the triangle, you're going to use the triangle to rewrite everything that you had in terms of theta for a final answer back in terms of x. All right, let's go back to looking at what we have here. So here's a triangle here drawn. Here x is the hypotenuse, a. The opposite side of theta is root x squared minus a squared. And this is where x is greater than a. And here I have, on this side here, I have minus a minus x, root x squared minus a squared. Here, notice that x is less than minus a. Okay. And we're going to need both reference triangles since the values of some trig ratios, meaning angles here, are different depending on whether the value of x is bigger than or equal to a or less than or equal to negative a. And that's why we have this absolute value here. All right, let's just go ahead and jump into an example here. Oops, went too far here. Find the area of a region. Find the area of a region between the graph f of x equals x squared minus 9 and the x-axis over the interval 3, 5. Okay, so here's my upper function, root x squared minus 9. And the x-axis, of course, is the lower function. And we're going from 3 to 5. So the area, here's the integral setup. Okay, and so we're going to go ahead and jump into, I've got the form that we had, and x is equal to 3 secant theta, and that forces dx to be 3 secant theta tangent theta d theta. And when I replace this radical with the x being 3 secant theta, and I have a minus 9, then what's going to come out of here is going to be, remember, a tangent theta. Okay. So this would be absolute value of a tangent theta, in this case 3 tangent theta, and then the dx will be 3 secant theta tangent theta d theta. So we're going to get 2 of these tangent thetas being multiplied, so we're going to have a tangent squared theta. And I'm going to get a 9 coming out because the dx will be give me a 3, and this radical will also contribute a 3. Okay. Now notice this is a definite integral, so I have to change the limits of integration. All right, so these were in terms of x, but I have a definite integral in terms of theta. So remember, theta is the inverse secant of 5/3. Right? So how do I get that? If x equals 3 secant theta divided by 3, x thirds equals secant theta, and to solve for theta, I apply inverse secant to both sides. So I need to take the inverse secant of 5/3 for the upper part here, and the inverse secant of 1 for the lower part. Notice it's inverse secant of x over 3. So here's 5 over 3, there's inverse secant of 5/3, and inverse secant of 3 over 3 would be inverse secant of 1, which is going to be 0. So you have to change the limits of integration. Okay. So now they're going to use, in this particular example, they're going to use a trig identity. Tangent squared theta is 1 minus secant squared theta. And so right here, they're replacing it with secant squared theta minus 1. There's the secant theta, there's the secant theta. And just to correct myself right there, shame on the textbook here, tangent squared theta is secant squared theta minus 1, so it's a typo there. But again, when you're doing these and you need a trig substitution, use the trig cheat sheet. And you can see here that tangent squared theta is secant squared theta minus 1. All right, so apologize for the textbook there, but they are using a form of Pythagorean's theorem and replacing tangent squared theta with secant squared theta minus 1. Now they're going to distribute the secant theta to each piece, so I have 9 secant cubed theta minus secant theta. And in this component here, the minus secant theta, that's in the integral table. So here's secant x. So that part here, this minus natural log secant theta plus tangent theta, is taking care of this component here. Now I am evaluating from 0 to inverse secant of 5/3. Okay. This secant cubed theta, here you have to use strategies from the previous section when I had powers of cosines and sines. Of course, this is 1 over cosine cubed. Okay, so I'm not going to go over the details there. You'll have to use strategies from the previous section. But once they evaluated this definite integral, this component, they got these pieces here. So that's left as an exercise of computing this on your own. Okay. So once they have that, they evaluated these from 0 to inverse secant of 5/3. Plugging those values into these calculations, they simply get 10 minus 9/2 natural log 3. So something to note, because this is a definite integral, you don't need to use your reference triangle anymore to go back. You would have to do that for an indefinite integral. But once you've changed the limits of integration, you just evaluate at these numbers. All right, so that concludes all 3 different forms. Remember, the 3 forms that we cover in this particular section will have root a squared minus x squared, root x squared minus a squared, and root a squared plus x squared. In all 3 of these cases, try to use substitution first or a simple integral table. That's generally the easiest way. If not, go ahead and use the corresponding trig substitutions for these. Make sure to draw the reference triangle so that you can convert back from variables in terms of theta back to variables in terms of x.